coming. As an incentive, as usual, for people who showed up early, let's do a bigger question. It's a poll. It's not an actual question. The question is, how many of you have done submitting project 1A in grade school? That's so A is I'm done, B is I'm not done. Sorry, what is Can you see? Oh, okay. Okay, so A is I'm done submitting. B is I'm not done yet. There's no right answers. It's a poll. Everybody done? All right. At least there's not much to think about here, so you should be done. Let's see. So A, it's 41%, 59% are not done. Okay, so deadline's 3 days from now, right? Another poll question. I'm not marking any right answers, so don't worry about it. Saying anything other than what the truth is. How many of you have actually done tip 1, project 1, of following through the hello world examples? This is very important. This is what I'm talking about. Okay? Let me explain. If you go to project 1, that's right here. This is project 1. At the bottom there's tips, facts, etc. So click here. Tip 1 is to try out these programming examples, which means going through the steps in this README, actually doing the steps in the README, reading it, doing it. The question is, how many of you have done that? Yes, A is I've done that, B is I've not yet done that. Should be about 80 responses. Click away. Okay, I think that should be good enough. 49% I have done that, 51% I have not done that. Okay, so it's an even split. Now, some of you who have not done that may still have submitted on Gradescope already and gotten a full score, or for your submission. I'll clarify the scoring a little bit as well. But I want to get started with topics for today. This is useful input. This is about 50-50, and the earlier one was about 41, 59, 40, closer to 40, 60. So I'll keep that in mind and then come back to project 1 FAQs towards the end of the class, okay? But I do want to get started with reliable data transport for today's topic. Okay. This is like a top 10, I'd say top 5 at least, actually, topic in networking. That is reliable data transport. Much of the internet traffic flows over TCP. We've seen that, right? TCP is a very important protocol. TCP is for that reason, and TCP is a reliable data transport protocol. Reliable data transport is not so easy. If you're struggling with project 1, you understand some implementation aspects of it. If you had a smooth ride through project 1, great, I'm very happy. But that tells you how to use a protocol that's already doing all the work for you. In this couple or 2 or 3 classes, we're going to learn the principles, the theory of reliable transport, right? We do principles first and then practice. So of course we'll look at TCP in great detail because that's the reliable transport protocol of the internet. But it's good to look at the problem in abstract, look at what are the different possible design choices you could have, and then look at what TCP simply does this, and this from the choices we looked at. So it's important to understand what the problem is, what are the options, what are the ways to solve it, and then look at how TCP specifically implements its design choices. Because that's one implementation, it's not the only time, right? Okay, so that's what we're going to do for a few classes, 2 or 3 classes. Why is this not working? Huh. Okay, I think it's working. So that's pictorially the representation of the reliable transport protocol, or reliable transport protocol design problem. You see a sender and a receiver, a sending process and a receiver process. This could be like your client and server, your client and our server in project 1, right? These are application level entities. The red line is the user kernel condition boundary. They are communicating over what is underneath them an unreliable channel, which is the internet, which is the IP layer, which is the net or the network layer. They need to provide the abstraction of a reliable channel on top of what is an unreliable channel underneath. So this is the way to, sorry, oops, I'm being slow. This is the way to think about it. There is a sender side aspect of a reliable transport protocol, a receiver side aspect of a reliable transport protocol that are giving your TCP application the abstraction, the look and feel, the semblance of reliability, even though the underlying network is completely unreliable. It can do bad things to bits, it can drop packets, it can do strange things, delay them, reorder them, whatnot. So this piece of code that runs in the kernel, it's below the application layer, on the sender and receiver sides, that is the transport protocol. So that's what TCP is doing. In project 1, you guys are using TCP. Right? You're not making or designing TCP itself. But we're looking at how TCP itself, or we are building the blocks towards understanding how TCP itself works. So that's the portion of the stack we're focusing on how to provide the abstraction of a reliable channel on top of what's otherwise an unreliable channel. And of course, the complexity of this design, what the design is, will depend on how unreliable, how bad is the underlying channel, which means what bad things can it do. We've seen some bad things that can happen, like corruption. Some bits may randomly get corrupted in packets, or inverted. It depends on the kind of channel. Packets can get lost. Another thing we've seen. Packets can get delayed, queuing delay, transmission, propagation, processing, all kinds of delays in the network. Some of these delays can cause packets to get reordered. So these are all the bad things that can happen. We want to accomplish reliable transport on top of this. And so the complexity of our protocol will depend on how bad the channel is. How many of these, which of these bad things can happen? Not all the bad things need the sledgehammer of the mechanisms that TCP uses or that we're going to see. If all that can happen is bit corruption, but not loss, you would expect a simpler transport protocol, reliable transport protocol to be able to handle it. If some bits can be corrupted and some packets can be entirely lost, that's a worse environment. So you would expect more mechanism in your reliable transport protocol. Okay? Okay. So the important thing to keep in mind while designing a reliable transport protocol is the sender and receiver don't actually know or can see each other's state. So this is how you need to imagine it. And to make it really clear that this is how you need to think about this, this is really how you need to think about it. It's a distributed system. the sender side, all it knows is its state. It cannot actually see anything that's happening on the receiver side. It has to infer the receiver's state, what you've received, what you have not received, what might have gotten corrupted en route. All of this has to be inferred by the sender without being able to just take into the receiver's state. So this is a little bit like long distance, just a phone communication. You don't have a lot of cues that you do in face-to-face communication. And you have to use the same phone line to communicate, to send messages like, did you hear that okay? Or what was that again? All of that has to go over the same unreliable channel and itself be lost. So we, as humans, when we speak on a phone line, we know how to recover from some of these things. We'll see that reliable transport uses some of these kinds of mechanisms as well, and some that of course don't apply to human conversation. So this is an important thing to keep in mind, that there is no way to know of the state of the other end except to send messages and ask them, or send them messages, ask them, hear back from them, and know what their state is, keeping in mind that these messages, this meta or protocol information asking, hey, what's your state, has to go through that same unreliable channel. That's what makes it tricky. Okay? All right, so, excuse me, sorry. We're back to the previous picture of creating an abstraction of a reliable channel on top of what is otherwise an unreliable channel. IP, or the internet's network layer, is that unreliable channel. TCP is giving you that abstraction to the application. We are going to introduce some terminology. You see 4 methods here. I think it's going to be a little easier for me if I try this today. So I can point without craning my neck too much. So you see some methods here like RDT send, UDT send, RDT receive, deliver data. Those are the basic methods. RDT send, RDT means reliable data transport. That's what we're going to be using this terminology here for. The app gets this abstraction. Whatever language you're using, it has a send method, it has a receive method in project 1, right? Underneath, the UDT stands for unreliable data transport. You can just think of it as IP send, IP receive. All you're doing is stamping an IP header on top of the packet and sending it out. Bad things can happen in IP. Okay, so those are the basic methods that are, the first set of most basic methods we're going to introduce, and we'll keep adding some more methods on top of this. RDT send is called by the application, UDT send is being called by the underlying transport, sender-side transport layer, UDT receive is being called by the underlying receiver-side transport layer, and UDT. And deliver data is when the receiver side gets this information and decides it's time to deliver it to the application. It may not deliver it right away. Some of you are learning this the hard way in project 1. Why may it not deliver it right away? Well, if things are not coming in order, you may not get it in order. You may not get something right away. It takes some time. Okay? So deliver data is called when the next in line or next piece of data arrives exactly as expected, and it's time to deliver that to the application. Okay, so what else is going on here? You have to keep in mind that this is a bidirectional communication channel. The transport protocols that we're going to look at, like TCP, these are bidirectional transport protocols. The channel itself allows for two-way communication. Right? Because bidirectional reliable transport protocols are harder, we're focusing first on principles. We'll start by looking at a unidirectional reliable data transport protocol, where there's a well-defined sender, there's a well-defined receiver. It's not like the sender and the receiver are both sending simultaneous data to each other. Makes the problem simple. So we'll look at that version of the problem in the abstract first before going to TCP, which is actually a bidirectional transport protocol on top of a bidirectional channel. The underlying channel is always bidirectional. You can send data both ways. You need to be able to send data this way, you need to be able to get some that's the application data being sent, that's the IP packet on the network layer. Like I said, we'll consider only unidirectional, and we will use an abstraction that you're familiar with. This is finite state machines, to describe protocols. Everybody familiar with finite state machines? Finite state machine is finite, it's a state machine of finite size. What's a state machine? It has states and it has transitions from one state to the other. When some event happens, you do some action and then jump to the next state. This is what a state machine is. The computer is a state machine. It's a Turing machine, a very powerful kind of state machine. Okay, there's lots of different kinds of state machines. The kind you're going to look at here is a finite state machine. It's very, very simple. Okay? So that's the notation we'll be using. When you look at a transition with something on the top and something on the bottom, a numerator and a denominator like thing, it means that when the entity that's executing this state machine is in state 1 and this particular event happens, it's going to take this particular action and then transition to state 2. Okay? This is a very common way of representing pictorially the state machine. Okay? Alright. So we will start with a very simple, trivial protocol for starters, so that you become familiar with how to just describe a protocol as a state machine. Why are we doing this? Why are we throwing FSMs, this theory and abstraction and all this stuff? Because it allows us to formally describe a transport protocol, a very simple transport protocol, much, much simpler than TCP. And reason about its correctness or lack thereof. It's very easy to make mistakes in the design of transport protocol. Correctness is important. Okay. Order, reliability, this all is a correctness property. Protocol either has it or it doesn't have it. It can't be flaky. It means it just doesn't have it. So if you want to guarantee in order reliable by-stream abstraction like TCP does, you better be confident in the design, the proof of correctness, the design of your protocol, before you even start thinking about the implementation of it. That said, finite state machines are incredibly useful, not only for theorizing about the correctness of your protocol, but also implementing it. It's very easy to take a finite state machine and translate it to code. It's very easy to say, be in this state. If this event happens, do this action. An action is just a bunch of instructions. Change your state to whatever the state is a variable, change your state to the next state. If this event happens, do this action. If this event happens, do this action. It's very simple to take this. It's very simple to take a finite state machine, and translate it to code. If instead of an FSM, you think in terms of the sender does this, okay, the receiver must have that, and so I must do this, the receiver will do that. Now you're thinking about a whole spaghettified mess of like an entire system into which you don't have insight. The sender doesn't know what's happening in the receiver. All it can do is, if this event happens at my end, this is the action I'm going to do. If you write this down for the sender, write this down for the receiver, you can then ask whether this is the correct protocol, or you can find mistakes in it. We will find some mistakes in some of the protocols we look at. Okay, so this first reliable transport protocol over an already reliable channel. This is just to get familiar with what the sender receiver FSM pair looks like. Nothing bad happens, no bit errors happen, no loss happens. It's not stated here, but no reordering or anything happens either. Okay? So you send a packet, it just goes in the order. We're looking at 1 bit, 1 byte, single packet transfers for now. Okay, so the sender is going to wait for a call from above. So this is like the socket.send, or any number of send methods in the programming language. They all have their different documentation, which you need to be very carefully before using it. Otherwise, you're going to make mistakes in transport, right? So this is the wait for call from above, which is the app is going to invoke some send method saying, here, this data, send it to the receiver. We are going to, so that's an event, RDT send data. When that event happens, the bottom is the action we take. The action we take is we packetize it, make packet. That's the method we're going to use to describe this. Okay, all of this is in the book, it's in the slides, so you don't have to take notes. What does make packet do? Well, in our case, we will just, in this simple protocol, all we have to do is attach the IP header, source address, IP destination, IP address. Other stuff in the IP header that we haven't learned about, we don't know about yet, we'll learn about it later. That's it, and then just write it to the underlying network. That's all the make packet is doing. The make packet is not writing, the UDT send is actually writing. Make packet is just attaching the IP header, UDT send is actually writing it. On the receiver side, you're going to wait for the call from below, whatever arrives from the network. We are simply going to, when this event happens, RDT receive, that means something arrived from the network, we're going to take the following action. We're going to extract the packet, which is the opposite of make packet, which means we just decapsulate the IP headers and get the transport level segment. And we simply deliver it to the application. This is what UDP would do. It doesn't do anything more than this. It attaches the IP header, sends, on the other side, removes the IP header, gives it to the app. Okay? UDP is unreliable. This is a reliable transport protocol. However, it's reliable only if the underlying channel is already reliable. So this is a no-op reliable transport protocol. It doesn't have to do any effort for reliability because the underlying channel is already reliable. Like I said, the only purpose of this, easy, the only purpose of this no-op reliable transport protocol is to illustrate how we're going to use some of these methods and how we are using the finite state machine abstract. There's one state at the center, one state at the center, just one state. So it's really, really trivial. Okay. Now let's move on to an actual non-trivial reliable transport protocol. We'll call this RDT 2.0. This was RDT 1.0, right? This was just a trivial one. There's nothing to do here. It's just for terminology familiarization. 2.0 deals with bit errors, the thing for which we saw checksums were being used. So internet checksums, we saw the ones complement sum of 2 bytecodes in the packet, right? So that's an example of a checksum. That can be used to detect errors, not perfectly. It comes with certain caveats. You may miss some errors, but if you catch some errors, you know for sure the packet is problematic. We will assume for this part, this session, that checksums just work perfectly. Okay. Checksums in practice don't work perfectly, but they work with high probability. For now, we'll just assume that they work perfectly. Okay. While looking at these two reliable transport protocols. The question is, how do we recover from these errors? So in this example, what do we add before sending a packet, after making the packet and before UDT sending it, as well as on the receiver side after UDT receiving a packet and before delivering? What do we have to do to recover from bit errors? So a natural question, you have a, well, yeah, you wanted to say something?
I thought you were asking.
Yeah, go ahead.
So basically, after we make the packet, then we just take data turned into text and put it into the packet.
Yeah, so this makes sense, right? What's your name? Jay. So Jay's answer is, well, as part of the make packet where you just stamp an IP header before, we want to insert the checksum. On the receiver side, we want to check the checksum. Yeah, well, that's fine. Well, that's right. But we need to put this into a state machine, finite state machine description. So it's a little more complicated to do the complete job of that. Okay? But that's the basic idea. We're going to use checksums, right? Well, before that, let's also ask this question of how do humans recover from errors during conversation? Right now, I'm speaking. Okay? You guys are just hearing, listening. I have no idea whether what I'm communicating is absorbing in your head, so I'm not for sure, right? How do I know whether it is or how well it is absorbing? we have homeworks and programming assignments and labs. This is the complete offline process of me figuring out how well you're on. Well, we have clicker questions in class to some extent. But I don't know whether what I'm saying is being heard by you fine or not. However, I have the luxury of in-person sight. I'm pretty tuned, I guess primarily by the experience of doing this for a long time. If I see lots of confused faces, if I see some people asleep, then I know that I'm being really bored, right? We don't have any of this luxury of being able to infer some of the state on the receiver side. With our transport protocol, we have a curtain. The only way I know whether you heard, you received something that I said, is if I get some information from you proving that you really heard what I said. We deal with this problem on phone calls all the time. We're pretty good at recovering from bit errors in phone calls. So sometimes, if you're speaking, you know, just making this up, you're saying, I'm going to be going to the mall. Okay? And if bit errors happen, maybe the other person hears it as I'm going up the hill or something like that. Well, they don't even rhyme, so it's not a good example. But you can imagine that a bit error happened, and somebody heard a word or part of the sentence you're saying incorrectly. Okay? This happens all the time. The noise happens in real world phone calls. If that happens, how do we humans recover from this conversation? It's not obvious what the algorithm uses. Sometimes what happens is the error stays and they think you said something, but that's not what you said, and neither party actually knows that you said something different and they heard something different. This can happen until like later they say, oh, I thought you were going to do this, and then you figure out that there was miscommunication before. Sometimes it's obvious to the other person that if they heard gibberish as opposed to another legitimate word, they're going to say, oh, say that again, what was that between these two words that you just said? I just missed that. And you repeat, and hopefully the second time when you repeat, they hear it fine. Lots of bad things can happen in this process. First, the second time you repeat, that may get corrupted as well. Also, they're asking you, can you repeat what you said between this and this? Could come with a lot of static. So you don't know that they're asking you to repeat what you said sometime back. All this interaction to correct bit errors has to also happen on the same channel, which can corrupt your correction-oriented meta or control packets as well. We somehow do a pretty good job of recovering from these kinds of errors in human conversation. Okay. The reliable transport protocol needs to do some of this. There are some analogies, some that don't have analogies to human conversation, but there are good analogies in reliable transport protocol as well. They have to be cognizant of all of this. Those control packets can also be lost. Questions like, can you say that again? And then saying that again, all of this can be corrupted as well. Okay, so like I said, we're going to assume checksums work perfectly. We don't want that nuisance right now, because even with perfect checksums, the problem is not trivial. It takes some effort to design reliable transport protocol. We're obviously going to use one of these two mechanisms, acknowledgement or ACKs, or negative acknowledgement, NACKs. To the extent possible, I'll try to not say NACKs and just say negative ACKs, because if I say a NACK, it often sounds like an ACK. Okay? An article and before ACK. So I'll say ACK and negative ACK. These are the two basic methods for a receiver to communicate to a sender that they received something correctly or that they did not receive something correctly. Checksums allow the receiver, perfect checksums at least, allow the receiver to determine that it has received something correctly. It also allows the receiver to determine when it hasn't received something correctly. Remember that the sender sends something, the receiver will always receive something. There's no loss here, only bit errors. This is a simpler network. This is not so bad a network. Loss creates more complexity that we haven't yet looked at. So if the sender sends something, the receiver will receive something. It can either send an ACK or a negative ACK based on the checksum, which we assume works perfectly, back to the sender to report so that the sender can determine what its next course of action. Sender is going to retransmit the packet if it gets a negative acknowledgement. If it gets an ACK, a positive acknowledgement, then the sender knows that the previous packet has been reliably transmitted. It can move on to the next packet. The kind of protocols we're going to see, the next three protocols we're going to see, are all called stop and wait protocols. What's a stop and wait protocol? The sender sends a packet, waits for some ACK or negative ACK from the receiver, then decides what to do, maybe retransmit the packet, gets completely done with that packet, and then moves on to the next packet. This is not the only kind of a protocol that you can have. I can send 3 packets out, and then wait for 3 ACKs or NACKs or some combination of them to trickle in, and then decide what to do. I don't have to send just 1 packet at a time and be all done with it. It has a cost. Fixing that is what's called pipelining, which we will look a little bit later after we look at these stop and wait protocols that are much simpler. The state machines for them are much simpler. The thing to keep in mind about state machines, let's say a sender and receiver, all the state at the sender and receiver, whatever data structures that they maintain, is 1 byte. So the sender state, this is the receiver. These are not states in a finite state machine. This is the sender and the receiver. Okay? A finite state machine circles have nothing to do with the sender and receiver. There's 1 byte of total state here. There's 1 byte of total state here. What is the state? It could mean things like 1 bit of that could store information about whether the most recent packet was received or not. Or if you have 1 byte of state, you can use the first 3 or 4 bits to keep information about which packets were lost, stuff like that. That's the state we're talking about. That's the curtain. Sender and receiver don't know each other's state. If the sender could have 1 byte of state, you represent this as a finite, the sender protocol is a finite state machine. How many finite state machine states do we need? Yeah? 256 states. That's 2 to the 8. There's 256 possible values for the state. A finite state machine tells you the sender, which state the sender is in right now. If what event happens, what action will it take and jump to which one of the 256 states or 255 other states? Or actually 256, it could remain in the same state also. So in order to simplify this protocol, we're looking at stop and wait protocols, where there can be at most 1 outstanding packet. So the amount of state that needs to be kept at the sender and receiver is just 1 or 2 bits of state. That makes the problem a lot simpler. That's why we're looking at stop and wait. Okay, so this is our RDT 2.0. The sender is waiting for a call from above. That's state 1. Or I guess we'll call it state 0 actually in these slides. When that event happens, the top thing, the event is app invoked from above us, RDT send. The action we take is to make the packet with the checksum like Jay said, and then UDT send it on the unreliable underlying channel. And jump to the state where we're waiting for an ACK or a negative ACK. Having sent it, resting assured that something will get to the other side. There's no loss, remember, only bit errors. We've sent something will go to the other side, and they will respond with an ACK or a negative ACK, and so something will come back to us. So we can wait there, doing nothing until that something comes back to us. That's our second state. In that second state, if this event happens, which is the event being I received something, and what I received is an ACK, then life is good. I do nothing and go back to my first state where I'm ready to send the next packet. This is the good case. However, another event can happen in that state, which is I receive a packet. It turns out to be a negative ACK. In which case, I'm simply going to retransmit the packet I most recently sent, which is QTP send. You could think about send packet here as the same send packet that was most recently created. Okay. Without counting that send packet information as part of the state. That's the function. There's only two states here. So we just retransmit the most recently sent packet. That's the variable send packet. And that's mostly it for the sender. What's the receiver protocol? Well, the receiver protocol is as follows. We're going to wait for a call from Billa. The packet comes in, if this event happens, RDT receive packet, and it's corrupt. How do we know it's corrupt? Well, the checksum. We just inserted a checksum right here, so we know the receiver checksums work perfectly. The receiver knows if checksums didn't work perfectly, this Boolean function corrupt won't return a reliable answer. But we're assuming it does. If you get something and it's corrupt, then the receiver is going to send a negative acknowledgement and remain in that one state. This receiver is going to be a one-state receiver. However, if this event happens, which is I get a packet and it is not corrupt, then I'm going to send a positive acknowledgement after extracting the packet, delivering it to the application. Because life is good, this is the good case. That's it. So let's look at this protocol in action. We've seen before. Let's look at this protocol in action. This is the initial state of the sender. When the app calls RDT send data, the sender would make a packet out of it by putting a checksum and send it over to the receiver side. And let's assume that in this case, this is the good case. Packet doesn't get corrupt. Receiver gets the packet fine. It's not corrupt. Therefore, it sends an ACK, a positive acknowledgement, to the sender, which makes the sender go back to the initial state by protocol, by the finite state machine description. Life may not always be so good. So this is the second case. Sender and receiver waiting these initial states. App calls RDT send. Upon that event, you, as usual, make packet after putting the checksum inside it and send it. And this time, it's bad thing happen. The receiver will get this packet as corrupt. You got something, RDT received and corrupt. It's going to send a negative acknowledgement to the sender. The sender is that's going to trigger that action on the sender. Got a packet and is not. At which point we will retransmit, and hopefully the retransmission goes to the good case, and we're done with the protocol. Right? This time it's a positive acknowledgement. So far, so good. Yeah.
What would happen if, like, if we were to mistake, like, if the receiver was sent back like a negative acknowledgement, but the sender mistakes that it was supposed to positive acknowledgement? Would that ever happen? Like, it's unreliable.
What's your name?
Chris?
Chris. Chris's question is, what happens if the receiver sends a negative acknowledgement and the sender mistakes it for a positive acknowledgement? So first, can this happen? How many of you think this can happen? How many of you think this cannot happen? No hands. Okay, the sender sends a negative acknowledgement, and that's going to come here or somewhere when the sender is waiting in this state at least. Sender gets a packet, and it's going to do is NAC on the received packet. In this case, when is it possible that the receiver sent a NAC and the sender thinks it's an ACK? In this case, it must be the case that checksums failed us, right? But we assume checksums work. So, if you receive a packet, and the packet's actually a NAC, but then the sender the sender ends up deciding it's a positive acknowledgement, not a negative acknowledgement. It means checksums wouldn't have worked. We're making the assumption checksums work. Okay? But there is actually a flaw in this protocol. The flaw, which I think Chris might have been thinking about or alluding to, this protocol, by the way, is not correct. Okay? I deliberately showed an oversimplified protocol to show why you need to be careful in the design of this protocol. This may seem like, okay, this seems fine, like a good protocol. Okay? This has a fatal flaw. That makes this protocol incorrect. And that fatal flaw is we're not checking in this case we're not even checking for corruption of ACK or NAC. This is a different point from my response to Chris that's saying checksums work perfectly. Here checksums do work perfectly, but we're not checking for corruption of ACK or NAC. So if you look here, on the receiver side, we're checking for we receive the packet and it's corrupt. We receive the packet, it's not corrupt. On the sender side, we are not checking if what we received is corrupt or not corrupt. We're missing the checksum check at all here. That's what makes this incorrect. Okay? That's the fatal flaw, which is what happens if the ACK or NAC is also corrupted, which we're not doing, like I just said, like we're doing for data. If we do that, then we can fix the protocol to be correct. That protocol wasn't even doing that at all. So there was no place where a NAC could magically become an ACK, because if you add this code for checking for corruption, it would catch, it would read it would read a negative acknowledgement as a negative acknowledgement, or know that it's corrupted. It won't think it's a positive acknowledgement. Okay? We don't need to fix this. So if an ACK or NAC is corrupted, we don't know what to do here in this protocol. In this protocol, it allows for, we got something, it is an ACK. We got something, it is an ACK. What if we get something and we can't make any sense of it? That's the case this doesn't handle. If that happens, the most natural solution on the sender side is to say, all right, I got something, I don't know what this gibberish is. I might as well think of that gibberish as a negative acknowledgement. Okay? If I get a positive acknowledgement, I know everything is good. But if I can't parse what I got, I might as well think of it as a negative acknowledgement and retransmit what I just previously or most recently sent. Retransmission was there in the protocol already, but we were missing a case, which is checking for ACK or NAC corruption. The moment you do retransmissions in any protocol, you have to worry about duplicates. You can't simply blindly retransmit data, even in a stop and wait protocol. What do I mean by detecting duplicates? Let's say the sender, in this case, was sending the receiver a bunch of words. Cat, dog, mouse, horse, and whatnot. That's our data. If a receiver receives the sequence of packets, the first packet cat, second packet dog, third packet dog, how does it know whether dog appears twice in this list or if it's a retransmission by the sender? It can know that only if the sender includes some sequence number information like 1. 3 dog after that, the receiver knows that, okay, the second word is a dog. The dog immediately following that is the third word. There is duplicates in the data itself. This is not a retransmission. However, if the receiver got 1 cat, 2 dog, 2 dog, it knows that this is a retransmission of the second word in the sender set. So anytime you do a retransmission, we've seen that for corruption, we need to do retransmission. Sometimes things can be corrupted, we fix that with retransmission. In any retransmissions, you have to have sequence numbers. This is the first lesson. It's probably a homework question that's in some way asks you this as well. The first lesson is we need sequence numbers to deal with retransmissions, which we need to deal with corruption. Yeah.
Just wondering, if you have the sequence number and you have a normal acknowledgement, could you just ask, like, was this sequence number a success? You don't have to go back.
Was this sequence number? Yeah, you're talking about, actually this won't be an optimization in practice, because asking and hearing back, even a small packet is going to take a long time. Propagation delays are not going to be non-present in practice. So let's not worry about optimizing the protocol. This particular optimization is actually not an optimization for most protocols. But yeah, that's, in any case, we're focusing on correctness here. So let's get the correct protocol first, and then we'll think about how to optimize it. There's any number of like big things to optimize, like pipelining and things like that first. That's where the low-hanging fruit is. Okay, so the fixed protocol, still a stop and wait protocol, that's RDT 2.1. Okay, this is the fixed protocol. RDT 2.0 that we just saw had a flaw. The 2-state sender, 1-state receiver is the wrong protocol. It looked fine, seemingly fine, but it wasn't. It didn't cover all our bases. This is a correct protocol, there's no trick anymore, okay? The sender has 4 states in it. These 4 states are respectively, or first 2 states are respectively, wait for the app to send data, and wait for the packet zeros, ACK or negative ACK. The other 2 states are for sequence number 1. So unlike this example of 1, 2, 3, 4, where the sequence number seems to be like an integer, that's many bits. Integers are 32, 64 bits on most machines. We only have a 1-bit sequence. All we need is a 1-bit sequence number to stop and wait protocol. So basically, it's going to be 0. Well, numbering starts from 0. Okay, 1 dog, 0 dog, 1 mouse, and so on. We just have a 1-bit sequence number. If you think about integers also work like this. They're just 32 bits or 64 bits, right? On any computer, eventually they'll have to wrap around. You don't have infinite integers. So we're just wrapping around up to this is the 1-bit integer, is what it is. Okay? That's just a binary integer. And this is enough, because as we have seen, if you use even 1 byte, you're looking at 256 states. That would be if you're looking at 32 bits for an integer, that blows up our state to like a really humongous thing, and it won't fit on a slide, right? 32 states is 4 billion. So we're looking at a 1-bit integer. That's our sequence number. That's enough to distinguish between duplicates versus retransmissions. 1 dog followed by 0 dog means there's duplicate in the data. 1 dog followed by 1 dog means retransmission. Okay, so we have enough to detect, to disambiguate between retransmissions and duplicates. So if the app asks us to send data, we're going to make a packet out of it with a checksum like before. UDT send it on the underlying channel, receiver, and a jump over to the state where we're waiting from the receiver for an ACK or a negative ACK. This is the life is good case. You receive something, and now we're checking, and it's not corrupt and is ACK, then do nothing, just move on. It's time to wait for the next packet from the application. We're done with this current packet. This is the life is good case. Same thing repeats here. If the application, if this is symmetric to the previous case that we saw, this whole thing is life is good case. So here, applicant asked us to send the next packet, we made a packet, sent it, here we got an uncorrupted positive acknowledgement, we went back and started waiting for packet 0 again. So we keep going, 0, 1, 0, 1. 2 states for packet 0, 2 states for packet 1. Waiting sequence number, the first state is waiting for the packet from the app above. The second state is waiting for ACK or negative ACK from the other side. That's why we have 2 states for each sequence number. This is only the good case. What are all the bad cases? Corruption at various places. Well, if you, in this state, if you get a packet and it's corrupted or is a negative acknowledgement, we're simply going to retransmit the most recent packet that we transmitted. A corrupted ACK or NACK or whatever message, corrupted message from the receiver effectively is equivalent to a negative acknowledgement. We just retransmit. We keep retransmitting until we get a positive acknowledgement that is not corrupted. Then we know for sure that the receiver has gotten out. Same thing symmetrically on the other side for sequence number 1. We're done with the same bit here. The receiver is a 2-state receiver. Wait for call from below, first state. When it gets a packet from below, and it's not corrupted, and has the expected sequence number of 0, which is what we're waiting for right now. This is the life is good case. Then we jump over and wait for 1. The next packet we expect is 1. We just got 0, we're waiting for 1 now. So we jump here. In this state, this is the life is good case. You receive a packet, it's not corrupted, and it has the expected sequence number, which is what we're waiting for. Then you extract, deliver, send an acknowledgement, or make an acknowledgement with checksum for the acknowledgement as well, so that the sender can detect corruption of acknowledgement, send it on the underlying channel. This is all life is good case. Where is the bad things happen case? This is an example of a bad thing. If you receive a packet and it's corrupted, then we are going to send a negative acknowledgement. We still need to do checksums, so these things can also get corrupted. There has to be another event handled here, which is if you receive a packet, it is not corrupted, and it has the wrong sequence number. This can happen. I am waiting for 1 dog, but if I get 0 cat, that must mean the sender was retransmitting 0 cat. So basically that case is saying the receiver got 0 cat, and the receiver was expecting 1 something. This name state was waiting for 1 from below. But instead of 1 something, it got 0 something. By design, the only thing that can be is a retransmission of what was sent most recently, because that's the sender second protocol. So it must be cat if it's 0. If this happens, you got a packet, it's not corrupted, it's the wrong sequence number compared to what you're waiting for, it is going to send an acknowledgement, a positive acknowledgement, for what it just received. So this is why are we sending a positive acknowledgement? Maybe the sender has retransmitted 0 cat, because the sender is not sure 0 cat got delivered to the other side, so retransmitted it. So the sender doesn't know that the receiver has received 0 cat, it received fine the first copy. So the receiver has to send a positive acknowledgement to the sender for sequence number 0 to tell the sender, oh, I got sequence number 0, the packet of sequence number 0 just fine. Okay? So corruption means negative acknowledgement, but wrong sequence number means positive acknowledgement for what you most recently got, so that the sender can move on. The sender knows that the receiver has received it. And then there's a symmetric side of those two for sequence number 1. Okay. This there is to a 1-bit or stop and wait protocol, a 1-bit sequence number protocol, reliable transport protocol, where the sender has 4 states, receiver has 2 states. We had to add sequence. Remember why we needed to add sequence numbers? We needed to add sequence numbers to disambiguate between retransmissions and duplicates in data. That's why we added sequence numbers. Anytime packets can get corrupted, they have to be retransmitted. Retransmission means sequence numbers. We doubled the number of states compared to our previous protocol. For each state 0 or 1, we had 2 states. One was waiting from above, the other was waiting for ACK or negative ACK from below. We also had to check if the ACK or NACK were corrupted. We did that. On the receiver side, we had to check the packet is duplicate, which we can know now through sequence numbers. And the receiver cannot know if what it sent most recently, an ACK or a negative ACK, was successfully received by the sender. The receiver doesn't know this. The only way a receiver knows whether it was successfully received or not is by looking at whether it is in the state where a retransmission happened. Here a retransmission happened possibly because the previous time it sent an acknowledgement, like here, that didn't go through. Right? So it can guess that last time I sent an acknowledgement, it didn't go through, but the receiver doesn't know this information for sure. That's our curtain analogy. You have to figure out what's happening on the other side strictly based on these messages, which also go over the same unreliable channel. We can make this protocol negative acknowledgement free. We don't need ACKs and negative acknowledgements. We only need one of the two. Okay. So in practice, acknowledgements is what we use. Negative acknowledgements are not needed. It's very easy. TCP also uses acknowledgements, not negative acknowledgements. It's very easy to fix this protocol to remove NACs, negative acknowledgements. How do we fix this protocol to remove negative acknowledgements? Well, we replace negative acknowledgements by simply an acknowledgement for the previous packet. So, if I'm waiting for one dog here, if I got 0 cat, I sent at 0. But if I got nothing, if I got gibberish, I would have sent NAC, negative acknowledgements here. Instead, I'm going to simply send, negative acknowledgement for 1, because that's what's mistaken or corrupted. Instead, I'm going to send an acknowledgement, a positive acknowledgement for the most recent packet. Telling the sender, that's all I've gotten until now, 0 cat. So instead of sending a negative acknowledgement for 1 that got corrupted, I'm going to send a positive acknowledgement for the most recent packet, implicitly telling the sender that it's a negative acknowledgement for 1. So here's how the protocol looks like. That's the part in red is the change in the protocol. If I receive a packet and it's corrupt, or this is the sender side protocol. If I receive a packet and it's corrupted, or is an acknowledgement for the wrong sequence number. I'm waiting for 0, I'm getting an acknowledgement for 1. I treat this like a negative acknowledgement. Because that's our contract. This is a NAC-free protocol. Then I'm going to retransmit the packet. If I get a packet, it's not corrupted, and is an acknowledgement for the right packet, 0, 0. We were not checking this. Let's go back and look at the previous sender protocol. We just said here previously is ACK. We were not checking the sequence number here. We didn't need to. This protocol is correct without that check. But if you want to make it NAC or negative acknowledgement free, we need to check that explicitly. Is it the wrong ACK or is it the right ACK? Wrong ACK, retransmit. Right ACK, life is good. Move on.
If the first packet was corrupted, then what would the receiver respond with?
If the first packet is corrupted, what would the receiver do?
Yeah.
I think I have the receiver fragment right here. It's going to send a positive acknowledgement for the most recent correctly received word. So if I am expecting one dog here, but I got gibberish, I'm going to send ACK0. ACK0, when I'm waiting for packet 1, is implicitly like NAC1. Because if I got the second packet 1 correctly, I would send ACK1. Why am I sending ACK0 again? Because I didn't get packet 1. That's why I'm retransmitting the ACK for whatever I got most recently. Yeah.
What happens if like the cat wasn't received properly? Like zero packet.
Okay, so the first one
Yeah.
here.
Yeah.
Okay, so let's say the 0 cat, let's denote this as corruption. Okay. Sender sends 0 cat, the receiver got something that it knows is corrupted because checksums work perfectly, right? So what's the receiver going to do? Its protocol is right here. So it's waiting for 0 from below. So it's waiting for 0 cat, received a packet, and corrupt or has wrong sequence number. Waiting for 0, got 1. It is going to UDT send packet. So it is going to send an acknowledgement for the most recent sequence number. What is the most recent sequence number here? It is going to send ACK1 because implicitly before the 0 is a 1. This is where the data started. But if this is the very first thing where there is a mistake, or there's a corruption, we want to send the ACK for the most recent packet. It would be the previous packet. I mean, you can, in integer space, with signed integers, you would think of this as -1, right? So that makes it easier to think of this as -1. If we had like positive, negative integers, you would send ACK -1 to say, that's all I got, I didn't get packet 0. But in our land, it's 0, 1, 0, 1 wraparound happens after one bit. So it's -1 is just 1 here. Okay, make sense? So that's what we said. If we get a corrupted packet or the wrong sequence number, we're going to retransmit the most recent acknowledgement that we transmitted. If we get a packet, it is not corrupted, and it has the right sequence number compared to what we were waiting for. We were waiting for 1 here, it has the right sequence number here. That part is not shown to make it simple. Then life is going to be extract, deliver, send back an ACK1 for the packet we correctly received, and the network. Yeah.
How is not using active beneficial? Like, isn't this just using 1 bit?
Yeah.
Using node?
It saves a packet. It's a question of, I mean, they're distinct mechanisms, ACK and negative ACK. And we're right now looking at principles, right? So it's good to understand what is the minimal mechanism needed. They are different mechanisms, ACK and NAC. And this is saying you don't need 2 mechanisms. You only need one of those 2. You just need an ACK and it'll work fine. Right? So this is the proof of concept. This is the correct protocol, correct stop and wait protocol. It's stop and wait, and that's the reason it's using 1-bit integers. Okay, more questions? Yeah.
Are we assuming that the sequence number can be corrupted?
No, we're just assuming checksums work perfectly here. So, that's a good, what's your name? Karen?
Kieran.
Kieran, yeah, that makes sense. Let's look at, explore Kieran's question and ask what happens to 06, I have about 10 minutes more. Which is, I think I have RDT 3.2. Let's say the first thing, instead of 0 cat, the CAT getting corrupted, maybe BAT, the cat didn't get corrupted, but the 0 got changed to a 1. We will not got corrupted, it's the same as cat getting corrupted. Checksums work perfectly. Okay, that's the assumption we're making. So if there's any corruption, the receiver detects it, and if the receiver detects a corruption or wrong sequence number, it's going to send retransmit the acknowledgement for the most recent correctly received packet. Okay, the last thing we're going to look at is loss, RDT 3.0. We haven't looked at loss in this protocol yet. can get lost entirely, it's much worse than you send something, something will get there. They sent back, they're going to send us back something, something will come back to us. If you can rest assured in this guarantee that if you send something, something will get there. It could be corrupted, it will be detected if corrupted as such. But the luxury of knowing if you send something, something will go to the other side makes life a lot easier than if I send something and nothing goes there. So on a phone call, conversations become easier if you say something and you know for sure the other person will either say uh-huh as a positive acknowledgement or interrupt you and say, can you repeat that again? The most recent thing that you said. What if you say something and it just goes into a vacuum, into outer space? It's pretty frustrating. What are you going to do? You're going to say, hello? Hello? Are you there? Hey, can you hear me? Are you there? Are you still there? Just cut, and you're going to pull your hair and then curse your mobile service provider. It's pretty frustrating. Right? So loss is a new bad thing that can happen in our network. And checksums, we need checksums, we need sequence numbers, we need retransmissions, all this is fine, but this is all not sufficient. How do we deal with loss? What do we need? Time out. What do we do when you're saying, hello, are you there? Are you there? Can you hear me? Is this call active at all? Anything? Anybody? And after a few seconds of this, we hang up. How many seconds? That's our timeout. We adaptively use the timeout based on human intelligence, but well, this is long enough. If I don't get back within between seconds, the call's probably cut. Okay? So the timeout is the mechanism, reasonable amount of time to wait and retransmit. Okay, that's our approach. Retransmissions may have still the duplicates, but we have sequence numbers to handle that, so that part is good. Timeouts, we're just using a countdown timer until a timer comes down to zero. The protocol becomes very simple. It's the same 4-state protocol with a timer. In fact, a timer actually makes some parts of handling corruption even easier. As before, it's 4 states, 2 for sequence number 0, 2 for sequence number 1. We only have a 1-bit sequence number, not integers. Wait for call 0 from above. These are the 2 states for 0. These are 2 states for 1. You send a packet as before and start a timer. Here, when you're waiting for this acknowledgement, if you receive a packet, it's not corrupted and it's an acknowledgement for the right packet that you for which you're waiting an acknowledgement. Before you stop the timer and move on to the next packet. Life is good. This is the other part of the life is good case, symmetric for packet 1. What's the bad stuff that can happen? If you're waiting for acknowledgement 0, timeout happens, that you get nothing, then you're going to retransmit the most recent packet that you transmitted. Send packet, restart the timer. If you get a packet and it's corrupt or is an ACK for the wrong packet, waiting for an ACK for 0, you got an ACK for 1. You know that ACK for a wrong packet is a NAC or negative acknowledgement. If that happens, you don't need to retransmit here. Because eventually the timer will expire and then you will retransmit here. Earlier we were retransmitting here, which the timer kind of obviated for us. So this becomes a no. This symbol just means no, do nothing, right? We don't need the retransmission we were doing here earlier in RDT 2.1. You can go back and check that. Or 2.2, sorry, you can go back and check that. Because eventually there will be you don't need to bother. I mean, at this point you know you could retransmit. You know that the ACK for a wrong packet means an ACK. You could retransmit, it won't be wrong. But even if you did nothing, eventually you will have a timeout and you will retransmit. So that's it, that's the sender side of the protocol. The rest is just symmetric to those. I haven't shown you the receiver side of it. That's, I think, one of the homework questions. So you've seen enough examples of receivers and senders. And one of the homework questions is the receiver side of this. Okay? Questions? yeah, we are pretending the state machine here is capturing only part of the state. Okay? We're assuming that states like timers, of course, they'll need, integers and much more information to keep track of all that. That's all not part of the finite state machine state. We don't care which, like, if the countdown timer is, suppose you're counting down from 20 seconds to 0 seconds. We don't care about whether it's 20, 19, 18, or so. We just care about whether a timeout happened or it didn't. So that's the safety critical, correctness critical part of the state. So we're only capturing that. But yeah, in the implementation, there will be much more state. Even if you implement just this protocol, there will be much more state than this. Okay. Couple of tips. Hang on. Project 1. I want to go back to this. If you look at this Piazza post, it only has 64 views, so I don't know how many of you looked at this. This was an exercise for you to do, to go over this getting started page, okay? I get a couple every day, at least, of requests saying, here's my code, I don't know why this is not working. Okay? It's true that programming assignment project 1A needs only tens of lines of code at best. It is not the first piece of socket call that you saw in the Hello World Python program that you can just put and expect to work because you think that's how it's supposed to work. It's not how it is. You need to read the documentation. This says two things. One, you take 30 to 45 minutes to do this exercise. This exercise is in Java. Doesn't matter if you're doing it in Python. Some students, I get comments like, yeah, I didn't do the Java part because I'm doing it in Python. I didn't think Java would be useful. Well, you're wrong. The problem with your code is not the language. It's the conceptual understanding of what a byte stream is. And this 30 to 45-minute exercise walks you through it. You don't have to program in Java to understand this conceptual stuff. Whatever language you're programming in, including Java, if you're going to use socket, send, and receive methods that you've never seen before in life, do not assume you know how it's supposed to work without reading its documentation. Okay? You can't just assume, based on looking at one Hello World example, that you're going to just use it the way it seems like it is supposed to work and assume it's supposed to work, and then ask us, why is my code not working? Well, most commonly the answer is it's not. It's working exactly as you wrote it. Okay? If you did this simple exercise of going through those Java examples and you read the documentation, you will be able to say, this is what I expect of the code to do, but it's this method to do, but it's not doing that. If you can get to that stage, then we can help debug your program. If you're not at that stage, it means you have just not taken the effort to go understand the conceptual part and the documentation of the socket API that you're trying to use. Okay? So don't do that. Do the exercise, read the documentation. Two most important bits. If you do that, 10, 20, almost 30 lines of code is all that you do. Very simple.